After seeing a little bit about the vectorial data and the raster data and how you can manage them in R, we are going to dive in the spatial correlation. So here we're going to use the SF dplyr packages in order to work with data, and we'll also be using the spdep package. This one is to validate a spatial dependence. So I'm going to load my packages, and I'm going to show the help of this package. And there are many available options. Many things can be done even with different areas. You can use this type of tools, the spatial tools. There are many available functions to convert one type of data to another type of data. So once again, this is the help so that you can look for anything that you need to do here. The first step that we're going to do is to read the vectorial data. This is the data that we saved in the first script. So if you don't find it in the folder, you possibly weren't able to run the first one correctly because we're using the data that was saved. So we're going to have a name. It's going to be called Chiapas, and you have the information of 118 municipalities and 11 different variables for the yield. So the first thing that I'm going to do is to keep the rows that have the data. So I'm going to remove all the other rows that have missing data, NAs. So this is the function, everything that has NA, not available data, for yield. And I'm going to filter this Chiapas layer. So now we would have 114 observations instead of 118. All of these have complete information. And as we saw in the theoretical part, the first part to validate this spatial correlation is to define the neighbors. So I'm using this function, polygons for neighbors, and I'm going to use the Queen criterion. This means that if one of the vortexes in one corner is shared, I consider it as a neighbor. So I'm going to create my list. I'm going to show a summary of the list. I already I showed you this in the theory. These are the amounts of neighbors that each one of them have. And the next step after defining the neighbors is that we have to define the weight. So I'm going to use this style called LW that allows us to maintain the neighbors as one with an equal distribution of weight. So this gives me this list, which includes the values in weight. This part isn't necessary for calculating spatial correlation. I'm just using it to create a map so that it's more clear what we're doing. So I'm going to read from inside out. So I have my vectorial data and my polygons in Chiapas, and I'm extracting only the geometry. That's what I'm interested in. And from the geometry, I'm extracting the centroid, which is the center of a polygon. And from this centroid, this function will throw me spatial data. And this will show me the coordinates. It's going to show me a vector with the coordinates or a matrix with just the coordinates, the x and y coordinates. And this is to use this function to create a map that requires the coordinates in this format. So I'm going to do an initial plot for the geometry. You can see the geometry from Chiapas here. We cannot see it clearly, so I'm going to put it in bold. And then I'm going to use the plot function with the list of neighbors and the coordinates of the center. So I'm going to add to this map that already exists, and I'm going to put it red. You can zoom in to see all the neighbors in each municipality. They're all defined here as neighbors. Some of them just have one neighbor, others that have several neighbors. Everything can be seen here. We can move and change the functions of the arguments to understand how this is going to change and understand what makes more sense for the analysis that you wish to make and how you would like to obtain those results. And continuing with the analysis, we are going to create a new column for Chiapas. And this column is going to have the average of the yield of the neighbors. So there's another function that's available that uses a list of the weight that I'm giving to each one of the neighbors and the variable of the point of interest that would be yield in this case. So the yield of the neighbors is equal to the weight that I attributed to each one of the neighbors. Sometimes the yield differs. So this gives us a new column. The last column would be the yield and the values. This is the average yield of the neighbors of each one of those points. Now I'm going to do a plot to see the yield values in each one of the points and the yield points for our neighbors. And with this, we can better understand the spatial correlation. So if I see this point over here, the yield in this point was approximately 2.6 and the yield of the neighbors was approximately 3.5. So this data has a clear correlation here. When one's larger, the other one would be also larger. And this shows us that there's a positive correlation. There's another easier way to do this with this function called Moran plot. So the objective is to calculate the IA for Moran, but for this Moran plot function, you have to do these three steps that we need in order to create the neighbors, the yield of the neighbors, and to create the plot. Now we can do it just with one step, with one function. This will be the Moran plot function. So I have the yield of Chiapas, the list of weights, and the configuration of the names of how I want them to be arranged. And you'll have the same plot now, but with additional diagnosis tools. And the angle of this line, this will be the relation between the value of one point and the value of the neighbors, is exactly what we're looking for. This is the trait that we're looking for on the spatial dependence. So if I use the Moran test function here with the same arguments, it's going to throw me that I for Moran has this value of 0.54 and that this value is highly significant. So there's no way to obtain this randomly, for example. So I can confirm that there's a spatial correlation in this data. And that was the objective when doing this, is to look for a metric that allows us to do this in a scientific fashion and to determine that there's a spatial correlation and that that correlation has this value, the I for Moran of 0.54. It's just like if it were a Pearson correlation based on the neighbors. In the SPDEP package, there are additional functions to calculate other types of metrics for spatial correlation, but I'm going to leave it this way just with this example that could be very useful for you.